for today's session. The online participants participating in our Design Safe channel. And today we have Engineer Pudleiner here with us to give the talk on complex bridge preservation in North America. Josh is the Associate Vice President and Assistant leading AECOM North American Complex Bridge Preservation Practice in Philadelphia. He is an industry leader in the design and construction of suspension bridge, main cable, and anchorage dehumidification system. Over 16 years of experience and has worked over 20 different suspension bridges throughout North America and Europe. More recently, in 2022, Josh was recognized as an ENR, Mid-Atlantic Top Young Professional. He's a licensed professional engineer in the United States and board certified safety trained supervisor in construction. He's a graduate from Penn State and Villanova University, where he completed his bachelor and master's degree. So help me welcome our guest here today. Thank you very much.
And I really appreciate everybody coming out. So back in 2007, something that wasn't in my bio, I was an undergraduate research assistant, and I worked between Fritz Lab and the Atlas Lab. And that really was the stepping stone for me to go on to graduate school, gave me a lot of experience. I had an opportunity to meet with Dr. Yan, the late Dr. Yan. This was probably the winter of 2006, and he was actually my father's advisor. He told me that in your career trajectory, if you want a linear path, that's more in line with getting just your bachelor's degree. But if you want an exponential path in your progress and success once you go out and either work or go into further research, graduate school is the way to go. So that really kind of gave me the stepping stone and the advice that I needed to kind of continue my education. So after that, then I started working for AECOM right out of school. So I'd like to just give you some background on my company. We'll start with the safety moment, go over AECOM as a global bridge team. We'll talk about the niche practice that I'm focused in, which is complex bridge preservation. We'll look at background of suspension bridges, some challenges and solutions that we see in the field. And then we'll highlight some of the key rehabilitation and preservation projects that I've been involved with and are currently ongoing with our practice. So safety, health, and environment here. Talk about working in close construction lanes. So this is during one of the airflow tests that we did on the Verrazano Narrows Bridge, and you can see what when we go out in the field, working in a close construction lane is number one for risk for us. So we're always trying to position ourselves behind a vehicle, away from traffic. This, as you can see, trucks going right by the adjacent lane. So really, I could share 20 different things that are on the top of my mind when it comes to safety, but that's number one when we're out in the field. And we do it quite often beyond inspections, pilot tests, different things like that, or when one of our projects goes to construction, which usually is a several-year duration construction project. The AECOM global team, we have over 1,700 bridge engineers located in 110 offices worldwide. In general, our company is 50,000 people in total. It breaks down then to the bridge global team. And then in North America, we have 610 in US and about 130 in Canada. So like I said in my abstract that I submitted, practice was started in 2015. It's led by Barry Colford. I'm his deputy. We're based out of Philadelphia. Our concentrations are design, construction, inspection, and we do get into asset management as well. Primarily focused on suspension bridges, but we also work on large truss bridges and cable stay bridges. Though cable stay bridges, their ages aren't to the extent of suspension bridges, which we'll get into in a minute. We work primarily in North America, United States and Canada primarily, but we have branched out into Latin America and to Europe as well. And currently we have 12 major projects going on, so it's keeping us pretty busy. pictures to the right are from my trip to Scotland last winter, or last summer, I mean, to look at the Forth Bridge, which is where my boss Barry used to preside and be in charge as the chief bridge master there. So to get into the complex bridge preservation practice, which is the niche practice I was talking about in the US, it's Barry and myself, Tyler Pritz. You can see all the names there highlighted, our core group out of Philadelphia, with Mike being out of Boston. Everyone else is positioned all throughout the country, mostly on the East Coast. And we pull from those resources as we need, depending on the job, as well as from folks in the UK. So, I'm sorry.
So Josh, you want me to minimize, or you know how to minimize the
Oh, sorry.
windows here?
I can do it, yeah.
Right there, yeah.
Good.
Oh, it is small.
Okay, you're perfect. Thank you. So I was saying, yeah, so back to our team in the UK. So, and I'll get into this, but dehumidification, which is one of the main technologies we're installing on suspension bridges, has made its way from Japan through the UK and into North America, mainly the United States. So our folks in the UK have vast experience, and they were involved with every job, including the first job of this being applied to suspension bridges in the UK. So they're invaluable. Mark Balmer has worked on over 40 suspension bridges throughout the world, really a technical expert. Here are some recent videos of us in action. There we go. So this is on the Newport Pell Bridge. This is during pre-design inspection. Walking the cables. This was last September. Getting some good views up there. Weather was nice. But as you can see, there's a tripping hazard right there as you send down the cable. So something you need to look out for. There's always things draped. When you're working that high, things usually aren't placed exactly where you think they should be placed if you just want to get it done. So there's things you have to work out for. And this was in October of last year. This is Barry and I out at the Hennepin Avenue Bridge in Minneapolis. The bridge is owned by Hennepin County. And it's a really vital bridge. There's an island that crosses that's in the middle of the Mississippi River here. This is the only bridge that you can use to access that island. And on that island, there's a high school. So it's pretty important, and they take it very seriously, keeping it in good condition. So background on suspension bridges. This is the Mount Hope Bridge, one of our current projects. It was built in 1929. This is a unique structure. That's why I chose to just kind of go over it here. So ultimately, you have the two towers that are out in the middle of the water. As you can see, you have the anchorages. In this bridge, it's unique because you have one anchorage on shore and one in the middle of the water. The anchorages are used to hold the cable in place and transfer the load down into the earth. You can see there's a stiffening truss, and the stiffening truss is hung from suspenders from the main cable. At the transition points where the main cable goes from carrying the deck to not carrying the deck, turns into what we call a backstay. There's a hold down configuration there on the pier as well. So the suspension bridge inventory in the US is aging as we speak. The average age is somewhere between 70 and 80 years old for structures. Ben Franklin Bridge, which I have had the really great opportunity to work on that for the past 6-7 years. It's turning 100 years old this July, and so it's a really great structure. Like I just showed you, the Mount Hope Bridge is turning 100 in 2029. So there are a bunch of others that were built in 1931. So they're all kind of coming of age. And here you can see the distribution throughout North America. Suspension bridges, a lot are on the East Coast and in the Northeast, a couple up in Canada. There are several though out throughout the Midwest and on the West Coast. We've had the opportunity to work on many of these shown here, which is really nice. So to get into suspension bridges and preserving them, the main non-redundant element of the suspension bridge is the main cable. And keeping it in good condition is of utmost importance. You want to keep the factor of safety as high as possible. You don't want to get to a level where you can't operate the bridge anymore. So to do this, we look at it through inspection, and we come up with preservation technologies and methods to try to keep it as in well conditioned as we can. So to look at the condition, to look at the construction here, we have one cable wire that are compacted into a circular shape. We have red lead paste, and we have helical wrapping wire. On top of that, then a coating system. And this was the traditional method of protecting the main cable wires utilized by Roebling on the Brooklyn Bridge back in 1883. So the main cable wires can be aerial spun, where you're taking one wire across back and forth from anchorage to anchorage, one wire at a time. And if you think of that, on the Ben Franklin Bridge, there's 18,666 wires on that bridge in one cable. So that's a lot of trips across the water using that system. There are a couple bridges, mainly the Newport Pell Bridge up in Rhode Island, and one of the Chesapeake Bay structures, I think it's westbound, that are prefabricated parallel wire, where those groups of wires already brought in like 61 in a bundle, brought across, and then compacted. And then you have helical strand, which is a twisted wire rope structural strand. And those are grouped together, and then there's spacers to put in to make it look round. Here's a good picture from Lehigh University and Fritz Lab back in the construction of the Ben Franklin Bridge. And this is testing of cable compaction. So this is in the original design book of Ben Franklin Bridge. It's really neat to see after several squeezes how those wires behave and take on a circular shape. And on the right, there's another Delaware River crossing the Wall Lemon Bridge back in the 50s, and that's how it's compacted out in the field using that contraption. After it's compacted, like I said, anything before 1970 is probably red lead, although red lead was used up until about 2000 in some locations. And now we moved on to Glycol paste, which is infused with linseed oil. And that's the George Washington Bridge back around 2018 getting rehabbed. Once you get that stuff on you, you cannot get it off, and try to avoid touching other places, and it just seems to spread if you come in contact with it. So everybody there is usually wearing tie-dye suits and strips down afterwards to get it out. You want to get that in your car or anything like that. After that is applied, and that actually acts as somewhat of a lubricant. Then we get into wrapping the main cable with the wire, the helical wire wrapping. Here are just a couple examples. My trip over there in the Fourth Road Bridge, Anthony Wayne, Tacoma Narrows out in Washington State. And then more recently, Simon Kent and Ben Franklin. So those are a couple from just the last several years. All different. The UK, I was really surprised to see the difference between a wrapping machine in the UK versus the United States. It's good to see. There's a lot more to it than the ones in the ones in the state are just built to get it done. So the ones over there, it's like a work of art. And then talk about conventional protections in the main cable. So after the wrapping wires on there, and you can see paint. Eventually the paint fails, you start to get corrosion of the wrapping wire. Cables have also been wrapped with a neoprene wrapping. However, wrapping it, eventually that fails just like paint. Now you're trapping the water inside. It's also tried to oil main cables, but oiling main cables, it's dirty, it gets everywhere, and eventually it becomes ineffective. So we'll talk about more wrapping. Here's an example of the Claiborne Pell Bridge. This was a prefabricated parallel wire cable, so it was the bundles that were then put together. And originally it was supposed to be aerial spun, but it changed. After that, they decided not to put a helical wrapping wire on, and just kept strap bands. And then they came on, and originally they put on a mylar bonder and methacrylate serum. So it's the same technology as if you went to get your nails done in the nail salon, but encapsulating the cable. After that, when inspections were done, things were repaired. They started using Hapalon wrap with a primer and a finish coat. And then flash forward to today, the more modern wrapping material, which we use to make airtight seals around the cable when we dehumidify air and pump it in there, is DS Brown cable guard. So this is an example of the Anthony Wayne Bridge of a cable that's wrapped but not dehumidified. And you can see the breakdown and the corrosion that occurred because eventually a part of that sealing system breaks down, water starts to get in, and now it's trapped. It was actually funny when we went out to look at this bridge during pre-design, there are actually pinholes poked in the bottom to let the water drain out because it was being retained, and especially at the low points as everything kind of converges to either mid-span or down on the low points on the side span. So that being said, here are some of the conditions of the main cables that we've seen in our experience out in the field doing inspections. You can see this is a bunch of broken wires at mid-span of one bridge. The cable bend saddle, you have a difference in mass between the zinc coating on the wires and the casting that it sits on, and you get a lot of rubbing there as well because of the cable movement on the bridge and the angle change during expansion and contraction. You start to get, you can see broken wires there on the bottom left. At midspan, wrapping wire failing. And the interesting story about that picture in the middle, that bridge, it's helical strand, and to make it round, it actually installed cedar fillers, made the cable round in between all the circular cross sections of those helical strands. And that cedar filler just soaks water up the spine. So now they have to go back. We're managing that cable, looking at it, inspecting it, and having to replace wrapping wire because of that. And this bridge is now actually scheduled to be dehumidified coming up here in the near future. You can also see at tower tops, it's very hard to seal at the top. The cable is continuous over the top of the tower, right? And it's very hard to seal between the tower top and the cable itself. And eventually things will break down and you'll start to get water in there. That's one bridge of many that have problems up at the tower. And then also anchorage interface going into the anchorage as well. In those trumpet castings you see there to kind of seal the cable as it goes into the concrete through the wall of the concrete anchorage, you get a lot of water in there as well. So we do internal inspections to monitor and check and look at the factor of safety of the bridge and ensure that it's in good condition, and monitor if things aren't going in the right direction. But we're basically watching it go downhill, and there has to be a way to either, we can't fix what's happening, but we can stop it at a point, freeze it, and keep it there before it gets down to a point where now you have to think about replacing the bridge or replacing the cables, which is just almost as costly as replacing the bridge. And eventually, if you don't do anything, this is the reality. This is a crossing, this is a twin span crossing over the Mississippi River in between Iowa and Illinois. And now it's being replaced with a tide arch bridge. It used to be two beautiful suspension bridges. So the bridges actually look pretty good, so it must have been a problem with the cables. But so how do we get to that point? How do we keep the cable from further degrading? And our answer is main cable dehumidification. Like I said, this was developed in Japan, made its way through Europe. It's been applied in the Middle East as well, but mainly now it started here in the United States back around 2013 timeframe. First two bridges that were dehumidified of the main cables and the anchorages were the twin spans of the Chesapeake Bay Bridge down in Maryland, and AECOM was involved with that as the lead designer there. So how does it work? Well, create a room, and that room pulls in air from the atmosphere, right? That air is then processed to a level of humidity below 40%. It's pulled out of the room through fans and through pipe work, and the cable is opened up when we put these sleeves on the cable where the air goes in and the air goes out upstream and downstream, and the air is injected into the cable, and that air then travels through all the interstitial voids of all those wires that are stacked up and compacted against each other. And basically we then, with that air going in, passing through and exiting, we're reducing the relative humidity within those areas below 40%. And we know at 40% that corrosion practically ceases. So that interstitial void in a normal cable is between 18 and 20%. If you add up all the cross sections, look at the difference of solid circle versus 18,000 wires up against each other. However, like I mentioned, there were bridges where oiling was applied as an anti-corrosive method to try to prolong and stop corrosion within the cable. And you'll see some pictures as I go through some of the projects, but in those areas we have a reduced cross section because of all the congealed oil. So we've developed methods of testing, putting air through the cable to try to determine before this project goes to construction how far we can move that air with the cable in where it goes in and where it exits. So this is just a schematic, again, using Mount Hope of the main cable dehumidification system. You can see the access that's built under the cable. So we build these OSHA certified platforms that the craft can work up to do the work and seal the cable, install different sensors, different sleeves, In addition, you can see the injection sleeve there up on the top right. Right there. Then you have the plant room. This is a unique plant room. This was under the deck of the bridge, but sometimes it can be a variety of different configurations inside an anchorage in a park. We put it in a bunch of different places. This is the ski master, which is used to install the wrapping material to seal the cable. You can see some of the dry air piping. This is used to inject the air into the cable. This is a list of and a graphic showing all of the suspension bridges in North America and the UK, currently, with constructed systems operating, currently in construction, or currently in design, or about to be put out for design. So there's a lot going on in the industry, and we've been lucky enough to be involved. I think with every bridge but Thousand Islands, which is a small crossing into Canada, in some capacity. Most of these as the owner's engineer, whether it was design, bid build, or design build, where the contractor then finalizes the design. So I'm gonna just talk about a couple of the key projects that we've been working on, show you some real life examples of what this looks like. The first and the biggest job that we've had is the Verrazano Narrows Bridge. This is a $250 million construction cost, over supposed to be 4 years, but the contractor's saying they can do it. It's supposed to be 5 years, and the contractor's saying they can do it in 4 years. So we're waiting and seeing if that can happen. Traffic is crazy on the bridge, but we are the owner's engineer here. We put together the conceptual design. In addition to dehumidifying all 4 cables, which I believe is they're wrapping 27,000 feet of main cable with this job, and this cable is 36 inches in diameter. So it's a massive, massive bridge. The towers at the tower top are over 700 feet above the water. So this is a really big structure. Everything you do here is magnified because of that, because of the size of it. Double decker as well. So 2 cables support the upper span, 2 cables support the lower deck. We're also replacing these cable band bolts, which keep the suspender ropes that the deck hangs from in place. We're looking at replacing the hand ropes and stanchion system, which is what I'm using there. As you see that picture, walking with the cable to make sure it's safe, that's getting replaced. And you can see one of our engineers, James McDowell, out in New York, senior level guy. He's running an airflow test here. We're pumping air through the cable. Here you can see the airflow test. We're checking to see, is air moving to this spot? Can we detect bubbles? And success. So if we know we can move it here with bubbles, we know once we seal everything effectively that the air will move much further. And once we finalize how far we can move it, finalize the layout of the system, you can see all the injection and exhaust sleeves there in the green and the red arrows. There's a plant room creating that dry air at each side. And then there's a schematic of what that plant room looked like conceptually in the anchorage. All the equipment, all the sensors and HVAC equipment. And put this size in perspective, those are full size vacuum trucks and they look like matchboxes. So the room there is going to be put in the green, but it's a very, very big anchorage, and we're building the structure for the room inside of the anchorage out of the way where it can then service the bridge. The next 2 are the Throgs Neck Bronx Whitestone bridges, and this is bundled together in a package. They may go to construction separately, but this is the same concept of what we did on the Verrazano Narrows Bridge. So there's going to be dehumidification, basically, replacement of hand ropes, cable band belts, all different things on here. And as well as a public safety fence along both structures, which HNTV is a substance for that. That's their specialty. Here we go is Throgs Neck and Bronx Whitestone. This is the pre-design inspection. That's James again, out of our New York office, walking both cables. Throgs Neck on the left, Bronx Whitestone on the right. Bronx Whitestone on the right has a lot of wind, issues with wind and oscillations. So anything you add to the structure has to be added, whether it's a platform, barrier, any of those things. You have to run wind tunnel testing to make sure that they can handle it. Next is Claiborne Pell. And so this is a very large project, and this is one of 3 volumes of work that are being done. There's work on the deck, work on the towers, some of the end compression links on the bridge. But we're involved with dehumidification and suspender rope replacement on here, as well as several other things, decorative lighting replacement. There were some issues with funding, with the increase in cost of everything today. So part of our work, the dehumidification would be in the future. We're still continuing to design on that, but we then refocused into the suspender rope replacement and some of the other steel work. And that's getting added on to a job that is going out for bid very, very soon. And so you can see here some of the challenges with the suspender ropes. This is a typical 1950s, 1960s connection of this is where the deck is basically hanging from the main cable. And on the left, you can see it's that type of socket it's a great structural connection, but it's inside the top cord. It stays wet all the time. And eventually it's very hard to inspect. You need a sweeper underbridge unit to go in and move out around and look up underneath. And so it's very, very difficult to monitor and to figure out, and to clean and to paint. Like once it starts to corrode, it's very, very hard to deal with. So we're changing the connection detail to a pin and clevis connection here. And that's going to connect on the outside of the main top cord of the stiffening truss with pin connections. And that way you can go and look at it at any time you want, any day of the week, and make sure that it looks like it's doing well. And to verify this, because there are issues with the stiffeners, as you can see on the left here, necking down, we're modeling the bridge, and we're looking at loading during construction of the existing stiffeners and those connections to see if we need to add any temporary stiffeners in there, especially when we start jacking the bridge to release some of these cables. And then we're also looking at the connection, geometry, stress concentration, loading. Next is Mount Hope Bridge, and this one's near and dear to my heart. So we're going from a 36-inch cable on Verrazano. This cable is 10 3/4 inch. It's like walking on a wet noodle. And there you can see where during the blow test, this is the airflow testing. This cable is also oiled, so that's why we're doing, especially doing a pretty significant airflow test on here. When we started wedging it open, that's what the inside of the cable looks like with the oil. So after we went through, you can see a temporary injection sleeve, got a man lift, a compressor, a fan, and a variable frequency drive for everybody who works in labs and knows what those are to control the fan speed. And so we're pumping the air into the cable, and we have some intermediate exhaust sleeves in some locations, and then sometimes we just trace bubbles because it has to be cost effective. So we do a little bit of each. Here you can see this is a sleeve that was installed. We were waiting to test, and the guys came back from the weekend after a rainstorm, right? And this is the amount of water that gets into the cable from one storm. Right, so this is what we want to prevent. And it just keeps going. Yeah, it's a lot of water. And we even resealed things to make sure it was like, as airtight as possible where we were testing. That's what it looked like. That's the amount of water. So here you can also see testing here. This is at an injection point, and then cutting into the caulking and looking for soapy water bubbles. So after we did that airflow test with the results at all the different locations we looked at, which was, I think we looked at almost 9 points, which is a lot for a bridge. And that was part of some issues that we had on another bridge that wasn't designed by us, but we were managing the construction. We said we need to do a lot there. It came out that max flow length was about 170 to 180 feet, which for this size bridge, that means that there's a lot of ejection and a lot of exhaust sleeves because the span is 1,200 feet. On the right, that's a picture of one of our schematics here showing the injection design drawing, showing the injection sleeve being installed on the cable, and how the dry air piping is up the suspender. So this started construction last September, and they've now mobilized in the field. I've built the platform. If you're using the bathroom there, I would maybe have some reservations. It's pretty close to the roadway there. If you can see that right there. I mean, when trucks go by, the mirror is almost clipping you. It's pretty tight. It's only one lane each direction. But now they're getting ready, they're replacing the cable band bolts, the big 1¾ inch diameter bolts, one at a time. So they're working on that, and I'm actually going up there next week to start off with the wrapping and sealing of the cable. So I'll probably be up there a couple of days each of the next 2 weeks. So here you can see some of the cable band bolt replacement. That's tensioning the bolt and then checking the tension by how much the bolt elongates. That's made by Squibb Custom Machines, which is used in Pennsylvania, so not far from here. They make almost all of the wire wrapping machines for the United States, as well as the we call these extensometers, but it's really just a big caliper that you use to, you know the length of the bolt, right? So you measure it when it's not stressed, then you apply and tighten it, and tensile force then elastically elongates it, and delta equals PL over AE, what force you have in the bolt. So it's pretty good stuff there. That job will be done then into 27 is what the projected to be. This is another bridge up in Halifax, is the Ingmar McKay Bridge in Nova Scotia. We've done numerous different things on this bridge since about 2021. Recently, we put together the main cable dehumidification conceptual design, but we've looked over laboratory work up at universities up in Canada, done some studies on bolts, safe span analysis. We also looked at the deck evaluation to see if they can redeck it. Here's some of the wedging work. And see some bird caging there, some corrosion. But biggest thing that we've done is the redecking feasibility study. This bridge has an orthotropic deck. It was built to last 50 years. The deck has a 5/8 inch thick top plate, which is below the current standard. And as you know, trucks keep getting heavier, tires are overinflated, and so there's these really high point loads being put on, and they're having fatigue problems with the deck. And so this is to look at, they're doing emergency, they can do an emergency repair and replace it, but it's very expensive to do it, and it's not feasible to do for the whole bridge deck for how long the bridge, I think it's like a 1,400-foot span, so from tower to tower main span. So we're looking at what they can do. Can they redeck it? They can't redeck it in kind. The cables can't handle a new code deck. A lot of things are under capacity built economically. So they're looking to see if they're going to build a new bridge or maintain this existing bridge, and we're helping in that study together. In addition, the other bridge that Halifax Harbor Bridge owns is the Angus McDonald Bridge. I can say one of our competitors designed the original system, but it has never fully worked properly on the bridge. So they've reached out to us to ask us to rehabilitate it and put it back into working order. This was something that dates back to about 2016. This bridge had its full truss and suspended ropes replaced as well back around that time. It's called Big Lift if you look it up online. And so this bridge needed rehabilitation. So we're looking at that right now. We're putting together a design build package for them so they can put out. Next is Simon Kenton in Kentucky. This is full suspender rope replacement of the bridge. This is actually in construction right now. We're going back and forth with the contractor for spills. We're changing the detail here. You can see so this bridge has a pedestrian walkway on one side and not the other. And the side that doesn't have the pedestrian walkway, there's a lot of collision issues with trucks hitting the stiffening, bearing stiffeners. Mainly, you can see there on the top of the left-hand side there, supervision. So we went out, we did an initial inspection. This crosses from Maysville, Kentucky to Aberdeen, Ohio. Pretty low population area compared to where we are here. Here you can see we're out in the field verifying the cable dimensions prior to making the wrapping machine. We did an internal cable inspection. This was last spring into the summer of 25. Did a little cable band bolt investigation to see what tension is in each of the bolt, and I can say we did find a bolt with 0 tension. So it was time to, there were no records of the bolts never being retention over the life of the bridge, which was built in 1931. So we said, I think it's time to do it when we do these other things. So we added to the contract that's currently being executed So you can see here some scaffolding layout, we had some visitors that one day. Nick and one of our local guys here looking at the cable as the contractor wedges it open. This cable was not perfectly round. And even with the spacers that they had, they added all different kinds of, ferrous plates that actually accelerated corrosion in some places that we found that we had to cut out. When we were trying to get in there to look at it. And then I could say putting it back together the way it was very difficult because of that. And we did find some broken wires. And so that's going to spur now future inspections within probably the next 5 years to take a look at additional locations. So here you can see some of the emergency repairs and the condition of the existing suspender rope configuration, and then the new pin and clevis connection that we designed that will be, again, similar to the one we saw on Blakemore Pell Bridge. Next is the hennepin, which I showed you up in the man lift. We did look at internal cable. This bridge was built in the 1990s, but it was never internally inspected, and we're now 35 years into its service life. At that point, you know that zinc is tailing off its effectiveness as galvanizing on the wires, and they've hit the end of their grace period, so it was time to look inside. So we did it. See the platform there mid span, taking a look. There are the helical strands that I talked about. So this had inner plastic fillers, and they were in pieces, so you could just pop them out. They were just kind of taped in place, and then there was a wrapping material over top, a half-long wrapping, which came off in 10 million pieces, which was difficult for the contractor, especially when you had to get it off those plastic fillers to get it back on and then rewrap it. But this is us taking a look at inside. And this cable will look good, but it's at the point where if you wanted to keep looking good, you need to do something. If you don't, you're going to start to get, brown ferrous corrosion. So we also looked in the anchorages as well. This is a picture of those structural strands being anchored into the anchorage and then post-tensioning rods around it, holding it in place. These also look very good as well. But we are replacing some of the dehumidifiers that are in there for smaller units. To get into this though, it's confined space, so you need to have tripod set up and an inch and everything. It's pretty involved. So try to do everything to monitor this because it's not remote monitoring. We try to put a display like at the manhole cover, so you can just pop the manhole cover off and take a look at the humidity level versus having to crawl down in there. All those things were kind of taken into consideration for that. Next is the Ben Franklin Bridge. This job started back in 2019. It's supposed to be its own project, just working on the cable, and then there were other things that came up, and they decided, well, if we make one mega project, then we can save on mobilization, and we can get these things done in a 5-year period versus spreading it over 10 or 15 years, one contract at a time. So our job was supposed to start in 2017. They actually got pushed to 2019 and combined with other steel repairs, decorative lighting replacement, rehabilitating the pedestrian walkways and widening one of the pedestrian walkways going in the canyon there. You can see where that white water tower is. That side of the pedestrian walkway got widened a little bit as well. So this job is still ongoing. Can you believe it? We had substantial completion though back 2025, and now we are in the process of monitoring the system for the next 4 years. So until 2029, we'll be involved at least, and we're watching. So it has the dehumidification system on the main cables, which we'll get into, and you can see there a picture of us during the commissioning of the system. Some of the engineers and our staff and the contractor as well. We all walked the physical work that was done on the bridge together. Take a look at the quality, make sure everybody was happy with it. And then we go into the system and we commission the system. So we turn the room off, turn it on several different ways, whether it's a fire alarm tripping in, whether it uses communication with sensors out on the bridge, all those things are looked at to make sure that it can recover and then handle itself once it's put out on its own. So that was a 2 or 3, it's usually a 2 or 3, maybe 4-day process to go through all those things, which can be a little mind-numbing after a while, but that's why I let some of the younger guys take care of the rest of it. I go for the first day sometimes, but yeah. So this is while they're building the platform looking into Philadelphia. So pretty high up there. That was an industrial painter installing that. Those are the A-frame tubes. After that, it gets the rest of the decking system. And in total on this bridge, we installed about 1.2 miles of that platform on both cables. So like I said, there were flow issues with the job. This was the job. Originally, we were supposed to build one platform, finish the job on that cable, then move over to the other side, and it was all choreographed with all the other things on the bridge that were happening. It's a $220 million job, and what happened was we got everything installed, got the plant room, creating the dry air, turn it on, start looking at the system, get nothing. Oh no, what's going on? Is it the piping? Is there a leak in the piping? Is the plant room not good enough? Is it the oil creating resistance in the cable? And so it turned out that the original design, designed by others, it didn't wedge the wires open with zinc wedges, right? To kind of tease the wires open for the air to get in. It was just relying on a longer sleeve surface area for the air to infiltrate. And this company has designed other systems, but they've been on newer bridges and never on a oil bridge. So there are all these things. They were pretty conservative with how far they could move the air, but it didn't work out. And what happened was when the guys were cleaning those wires and all that oil and lead and things off of the main cable with a hand tool, because you have to be very careful on the wires. They're actually pushing that material into the interfaces where the air is going to pass in, right? So basically, we had to think about what we're going to do. How do we fix this? Well, we had to buy material for another platform. We had to secure, this is a Department of Homeland Security asset. So we had to work with Homeland Security to secure the existing platform. So nobody, once we walk, so it's a pedestrian walkway on both sides, nobody can get up on the cable because people climb the cable for fun. And so we had to orchestrate all of this and then go back, take all those sleeves off of the cable, install zinc wedges in all these places to tease the wires open, and then go through troubleshooting. So we had to do troubleshooting beforehand, after, during. It was a whole year of basically troubleshooting while all the other initial work was starting to be done on south of the second cable. So it was a really, really tough job as far as that goes. But I think it was in one aspect. In the other aspect, we learned a lot from the issues that we had to get through, and it kind of gave us experience now going forward, working with other oiled cables or other locations, what we need to do, how we can handle it. So this is I don't know if I showed a picture of this actually in any of the other than maybe one of the initial slides, but this is the elastomeric wrapping material getting applied to the cable. Once this is applied, then it's heated on and it fuses together. And then all the interfaces where you see behind those guys wrapped in cling wrap right now to keep water getting in, but that gets all caulked and everything as well to make it as airtight as possible. So one other interesting thing on this bridge was the wire repairs at midspan on one of the cables. So we repaired about 185 wires on one of the cables, one wire at a time. It was almost like dental surgery. So, and because you need, at the end of the day, you need to make the cable has to be round again. We had to take one suspender off, so we had more room to work. And so all the ferrules and all the splices we made of the wires to repair them all had to be spaced accordingly so that when we recompacted everything, we could get the cable back together the way it was supposed to be and put the new wrapping wire on. And the new suspender ropes on and the wrapping wire. And the suspender ropes we took off were originally supposed to be put back in place. However, during construction, we said, when's the last time you tested ropes since they've been replaced, which was like in the 1980s. They said, never replaced. We never tested ropes. We said, this would be a good opportunity to do it. And so we linked up with Atlas here at Lehigh with Ian and put together, and at Fritz Lab, and we put together a plan, fabricated some fixtures and tested some of the ropes. We'll see that here in a second. Here we go with some of the ferrules. You can see how they're all spaced out, so they're spreaded. And the other press-on ferrules, the regular ferrules, This is so our guys would go in there. This is a very, very coordinated effort with the contractor to identify five like wires. Wires, once you replace them, can't cross either. And you're 40 feet apart from each other. So it takes very, very meticulous procedure to go through this. This is at the end of the day before it gets put back into place. I think some of these wires either got snipped or got held back in as they put the wrapping wire back on. Some wires can't be saved or repaired, especially if they're too close and you can't grab onto them with a come along. So in addition to those wire repairs, this is what the room on the Ben Franklin looks like inside that creates the dry air. This is a kind of a crazy layout if you ask me, but all the air is made in one of the anchorages and it's piped all the way across the bridge. It has one main trunket. So there's valves that are used to balance everything. It's like a pipe organ, and it was very, very difficult to get it to balance out, because if you think about it, this is also supplying air into the anchorage chambers on the opposite side of the river. So the air is just dumping out the end, and you have to kind of create a back pressure and then adjust each one as it goes. Basically, you get a lot of pressure in the beginning, and it really drops off. So you have to close the valves closest to push the air further. But this is what it looks like. Then this room also circulates air between the display chambers where the cables are anchored in the Philadelphia anchorage as well. So this is that dry air pipe I was talking about. And this had these Fernco couplers, which I would never use again in my life, but we had to put them on here anyway. You can see how there's issues with it lining up here. This part was fabricated in Reading, Pennsylvania, and this part was fabricated in Canada. And so when they came to the job site, they didn't line up very good. And then we had this flexible coupler. And so we had to go back out, ream holes, adjust things and get it, into place. And I think eventually we did make it look better than that, but so those are some of the initials. And then again, the pipe fitters here, you can see that this flexible coupler here is just maxed out, right, to the one direction. Originally this was on like a 15-degree slope, and this really should have been welded because there's more Fernco than stainless steel pipe right here, which is, in my opinion, the issue. Right here, this is in the room where the pressure is the highest because the air is being sucked with the fan and going up out of the fan through here. This should all be solid, but we had to follow the contract. So unfortunately, we might have to go back and fix that at some point, but there we are. And this is the oil inside of the cable. This is the worst cable we've seen as far as the oil and the congealed red lead and everything that's in there. So really needed to be wedged over. This is part of the wedging, what we found when we opened it up. And after we got the system operational, wedged, this is up on the platform, popping a drain plug. You can see water coming out, which is good. So as the cable goes through a drying process, the water will accumulate in the bottom of the exhaust sleeve for any of the water that will naturally just follow out with the exhaust air. And every once in a while during this period, which could be on a normal bridge, maybe the first year, for this bridge, maybe the first couple to 3 years, during like their biannual inspections, you can go out there and be lift and go and pull these drain plugs if you see the relative humidity level is high in these spots. And that'll accelerate the drying out of the bridge and the cable. So here's the suspender rope testing we did at Fritz Lab with Ian, and we used a 5 million pound machine. We fabricated these custom fixtures here. We really tried to replicate what the suspender was, how it was being, like the geometry it had while it was in service, its configuration, right? So we made a gatherer. A lot of times these ropes are diced and they're cut and a new socket's put on and a straight pole, they're pulled and the legs are parallel. Here we used a gatherer, and Ian, I know, reinforced that gatherer so it wouldn't be the weak point of failure. And we put this in place, and I think we made it just under 1 million pounds for each test. So the failure was pretty explosive. There you can see the video, and we're taking a look post-testing what it looked like. We had the client, the Delaware River Port Authority. You can see us there on that. balcony right there at the testing machine. Elevated platform, so worked out really well. In addition, the hand ropes were something that came up during construction on the Ben Franklin. See some of the condition of the bolts. The connection just wasn't tight, so water was getting in there. Again, we went up to Fritz Lab and we made 20 samples from one of the existing ropes. These ropes are 100 years old. So we tested these up in the lab and we got a couple low tests, but we did get a decent capacity. The client's gonna program this into its replacement at some point in the future. So now, like I mentioned, we're involved through 2029. This is part of the monthly maintenance and monitoring of the bridge. We look at the data, we go out, change filters, look inside the enclosures that have all that's where all the sensors report back to and get connected to the network. It's all SCADA panels. There's PLC probes in there, uninterruptible power supplies, fans, all different things, lights. So we just wanted, there's an outlet usually in one of them too. So you want to make sure that there's not water getting in, nothing's overheated, everything looks like it's supposed to be. This is what the output of the system looks like. This is the Ben Franklin, but we have this on numerous projects. This is showing the anchorage enclosures in each anchorage. You can see right here, right here. We also have, this is what's going on inside the buffer chamber, that big room I showed you with all that equipment. You know what, so there's a primary and a backup for each of the dehumidifiers and fans. One only operates each at a time. So then it just shows you the status. So you know what the relative humidity is inside the room and the temperature. And out on the bridge, this is at each sleeve, or we also have some monitoring points where it doesn't exhaust, the air just passes through. It'll show you the temperature, relative humidity, flow, and pressure as well at both. And if any alarm go off on the system, it shows up here in a log, but it can also get hit with a email or a text message depending. It'll tell you what the issue is. It needs to respond basically. You can toggle through. This bridge has so many injection sleeve. This is just showing that yellow box there. If you change the Camden Tower, it'll show you what's going on in New Jersey. Then you can look at what's going on inside the camera. And power, the map monitors the power, how much power the room is strong as well. The last one I wanted to show is because this is beautiful historic structure is the John Hoagland Bridge. And we've been involved with fracture critical inspections for KYTC. They manage all the major Ohio crossings. This is one of the essential ones. This was back, let's say 2024 timeframe, late 2024. But yeah, just the layout and the architecture. This was really the precursor to the Brooklyn Bridge. And it probably learned a lot from this bridge and ended up making some changes in this design, I believe, to implement it. He did Brooklyn Bridge, mainly because he added a second main cable up here and here to then added more stays and put in suspenders to better support the deck. So here you can see some of the guys out of the office. They're all rope access, Sprat Jedi Masters, I call them, because they have so many hours in the field, how they can get it. But you can see some of the connections here, the corrosion that's happening on the suspender rope. So I foresee there's probably going to be an internal inspection and some suspender testing here at some point in the next couple of years. So as I say, the suspension bridges always keep it interesting. We found, like I said, in Kentucky, these filler rods inside of the cable, which we weren't expecting. You can see that cable band bolt looks like a blooming onion with all the corrosion there. When you actually go to take that off, you need the lower size socket because so much metal has gone away. On the top right, this is at one of our jobs on the Anthony Wayne Bridge. We found a bullet. There was a leak. What's that hissing noise? And we go out to the cable, and there's it's like a 357 Magnum shell in the cable, and we're like, what is going on here? So we don't know how it got there, but we had to go back and patch that, which was pretty interesting. On the right, you can see that column that used to be there when there's water infiltration in this anchorage. they demolished the concrete walls that encased it. And when they took it off, there was almost nothing. Thankfully, there's a lot of other redundant. It wasn't carrying a lot of load, and there were other columns nearby, so it could kind of spread out. But this was repaired. And then this was another one where they usually this wrapping wire gets terminated up top. This was found to terminate in the cable band, which is really odd. And when you're trying to keep air inside, this causes now you have 8 leaks on a cable band, right? So this had to get fixed to make the system to wrap it and seal it effectively, and cost about $800,000 to fix all these throughout the bridge. There's like 354 locations, four holes of cable band, you know, so it was pretty major, but it was an early action. We said we gotta just push through and keep the job on schedule, so it was done. And with that, thank you for your attention, and we'll turn it over for any questions or comments that you may have.
Thank you for such an incredible presentation. This was amazing. So questions for our guest speaker today.
You talked a little bit about how there can be water infiltration kind of connections. You have all the trumpet guards or
Oh
something.
yeah, like something to casting or
Yeah.
there. Yeah, sure.
Will water or humidity ever penetrate through like the edge of the concrete itself? Is it or is it it's not like a very fine base. So does that ever happen, and how do you address that?
Yeah. I mean, suspension bridge anchorages are one of the most difficult things to seal. I can't think of an anchorage I've ever seen that have some sort of issue.
Yeah.
Either because the condition on the outside is much water in, or like you saw that casting. That luckily was like a localized issue, right? And when they opened it up, the wrapping wire was corroded all the way through, and they're like, oh my god, and it's very close to the wall there, so you don't have a lot to work with to like grab on to repair. So it could have been major, but luckily when we spent about, I don't know, $35,000 at the time, this was 2019. Built a scaffolding, went in, opened it up. Everything beyond that, like the outer layer of wires, was still in great shape. So it's just a localized thing. But yeah, I mean, I've seen anchorages where every time it rains, there's a waterfall coming through from somewhere, and they're like, oh man, So dehumidifying those are very important. And sometimes that involves, depending on the size, it can involve, if it's smaller, maybe you have to fix some of those issues on the outside, and you can dehumidify the space inside. Usually those walls are like 3 foot thick, so once you fix the issues, it's kind of containing is okay. But if it's a really, really big structure, and you're not going to pay to dehumidify this whole room, if this computer is your issue, you can build a shroud or a rigid containment around where that cable comes in and anchors, and then you can just dehumidify that space. Right? So there's a lot of different methods and ways to go about it. Thank you. Yeah, good question. Thanks.
Josh, is there a difference in a dehumidification system for a new bridge versus something existing, or is it based on the same technology?
It's the same technology. It can vary. Older bridges typically with corrosion, maybe they've been oiled. The distance you can move air is most likely less, so could be a little more costly because you're starting from, this bridge has been out there 99 years, and now we're putting on, or 100 years, and you're putting on the system. You may have to fix other things in the meantime, but really it'll most likely would be that the air won't as far, so you'll require more injection, exhaust sleeves, more sensors. So just kind of that way it'll might be more costly.
Thanks.
Yep.
Question.
When you guys had the issue with the one main cable, was that the microwave?
Yeah.
Did Did your PA help you out at all financially, or did you have to eat that cost?
Yeah, oh yeah, it was scheduled in there, yeah, so yeah, it had to be, it had to be done, it was part of the work, so, which is a good thing, and now, I mean, that's a big, repairing that many wires is a really good thing, for the cable, so now it's dehumidified. We could tell that, you know, based on the oiling that was done, it definitely helped the situation, but it was, you know, after so many inspections proved that things were still kind of, you know, slowly going in, you know, the downward direction. It was like, it's time now to put the dehumidification system on us. Luckily, that bridge, because it takes rail traffic, pedestrian, and 7 lanes of vehicular traffic, and the area that was built in, it had a lot of factor of safety built into it when it was first constructed. It's a heavy bridge, but you know, normal bridges have a suspender of say 40 to 50 feet center to center. This bridge has it every 20 feet. So there's like, it's like owning a V12, you know, a car with a V12 engine. Everything you do on that bridge costs 3 times more than what you did, you know, on another bridge because of all sealing, wrapping and stuff had to get done. But it really, yeah, it worked out well.
Can you identify some patterns that are completely different from bridges that are in marine environments from bridges that are just like exposed to the everything?
Yeah, for sure. I mean, if you look at the cables, I mean, I haven't personally looked at some of these, but I've looked at some, but not all. Bridges that are in saltwater environments, a sandy environment, have many more problems typically with steel corrosion of the main cable, than bridges that are over freshwater, say like the Mackinac Bridge or bridge in the Midwest that isn't exposed to that. So Anthony Wayne is kind of a one-off. You know, so it's a very industrial town. Could be, you know, a lot of pollutants there that are accelerating some of that as well there. You know, with glass being, and I think everything under the sun used to be manufactured there, and it crosses over. You look at the river there; it's called the Muddy Mommy because it looks like a muddy puddle 24/7. You know, so it's just the area I think is conducive to that. But yeah, some of the other ones that are over, like even the Hennepin Avenue Bridge, or saltwater, you would expect based on the climate there that it would be worse condition than it was, but we would fit out of it. It was really good conditions. So, yeah.
No questions. I have one last question, and because we are within the marine universe,
Sure.
is there any particular considerations for your system due to the local natural hazards that that bridge may be exposed to? Not the bridge itself, but to the system that you guys use.
But install, pretty well. I mean, we expect when that system is installed that like the physical wrapping and sealing will last at least 40 years on the cable. We make the sleeves that inject and exhaust the dry air out of 316 working grade stainless so that it will have any issues with those corroding. The sealant that we use is a really high grade adhesive sealant. So that's installed. It's a fast cure, so you can install it. It'll skin over pretty quickly, and then you can come back and do your second lift right away. That is like rock hard. So once that's installed, that you have no worries of that fan release, which is good. And then the piping we use is HDPE piping, and that's allows us to. You saw stainless in that one job, but in the projects we designed, we use HDPE. That can be brought in on spools. You can pull that out in hundreds of foot sections at a time, reducing the number of splices you have. The black is UV resistant. We typically try to put the main lines of that piping under the deck, so that's protected from carbon on, you know, like UV and something. Sure. You may have to replace the galvanized and coated. You know, usually these pipes, because HDPE is flexible, so you have to run a messenger wire and latch the pipe together to carry it. So those kinds of things may have to be replaced at the time, but those should last at least a year. And
Anything else? Speak now, or? No. Okay.
All right,
Well,
thank you, everybody.
thank you so much.
We have brochures here, if any of you are interested. Some pictures look similar to the presentation, but as you're walking out.